As I said, you can use Taylor series to solve a differential equation as well. And here, using Taylor approximation, we can come up with the approximation for anything that is given to us. Now, using the terms that we've been talking about in this lesson, to use Taylor series for your approximation, you can technically use this equation here plus y prime, or technically f prime, so that it looks pretty much the same as what you did in the previous chapter. And here, this would give us the step length times it by h plus f double prime x0 divided by 2 factorial times it by the square of your step length. And then as you do the same thing again and again, that will give us what we call the Taylor approximation for your differential equation. So here in example number 2, if I want to find a third degree Taylor polynomial to approximate the solution for some random point using the differential equation here, we need to start from somewhere. This is where we are starting, at x equals 1 and y equals 0. So here, starting at the beginning, this is what we're having. Y equals f of x, or f of x equals y. So technically, we have this result. And then, using the Taylor approximation, we are going to make use of f prime of x, or f prime of x0. We have the equation as well. This is basically what is given, x squared plus y squared. And then the Taylor approximation involves y double prime and the triple prime as well. So coming back to this, I need to differentiate this function for the second time, and then differentiate it 3 times. And we are going to use chain rule or whatever it is to differentiate the function. So knowing how we have f prime equals x squared plus y squared, differentiate this with respect to x, we end with 2x from the above. And then as I differentiate y squared, it becomes 2y times y prime. Or technically, knowing how dy dx equals what we had in the previous case, we are going to make use of that result at a later time. Or of course, you can simply replace the dy dx in this case using x squared plus y squared. And finally, as I differentiate this for the third time, 2x becomes a 2. And then, as I differentiate this, we will be using the product rule in this case. We are going to get 2y prime, differentiate the first part, and leave out the second part here, f prime times g plus f times g prime, which involves differentiating the function twice. And once again, this result can be obtained from the previous step as you differentiate your function 2 times. So based on what we have here, we have x equals 1 and y equals 0. And then, as I differentiate this function again, using the same value for x, once again, the Taylor series involves using the same x value for all these derivatives. I have x squared plus y squared, and as you calculate it, we have 1. And then for f double prime, we will end up with 2 times x plus 2 times y times dy dx, which is the value from the above. And that's calculate to a 2. And finally, triple prime when x equals 1 involve 2 plus square bracket 2 times 1, that's dy dx, times it by 1 again, plus 2 times y times the second derivative, which is the result from the above, and that give us 4. So altogether, if you want to calculate the value when x equals 1.1, using the Taylor approximation from the above, it involves using this, which is 0, plus f prime of x times it by the step length. F prime of x times it by the step length, which is 0.1. 1.1 compared to 1, this is the x value, your xy equals 1.1, and this is where you're starting. So the step length is 0.1 plus derivative second derivative divided by 2 factorial, second derivative divided by 2 factorial, times it by the square of your step length. And as you continue, triple prime, that's 4, divided by 3 factorial, times it by 0.1 cube, that's the third degree Taylor approximation. And putting all of these into your calculator, we can then come up with the answer round to 4 decimal place, or technically 0.1107.